a proxy model of MASH for liver conditions and its relationship with 5 biomarkers, using VMT energy analysis, a systems-based perspective. Number 1289, VMT Sharp 663, March 31, 2025, 5,300,000. Gerald C. EclaireMD Foundation. Category: Liver complications. Abstract: a proxy-based model. A proxy-based model is a scientific method for estimating an unknown, or hard-to-measure variable, using measurable indicators that are strongly correlated with it. A proxy is a substitute, or stand-in used when direct measurement is impractical, unavailable, or invasive. In this biomedical study, the author investigates metabolic dysfunction-associated steatohepatitis, MASH, a form of fatty liver disease, without access to direct clinical data, such as liver biopsy results, ALT, AST, GGT laboratory tests, FibroScan assessments, or MRI-based liver fat measurements. Instead, the author leverages his collected and calculated long-term, high-frequency metabolic data, including visceral fat percentage, VF%, fasting plasma glucose, FPG, estimated average glucose, EAG, blood pressure, BP, and blood lipid levels, triglycerides, TG, as proxies. These 5 indicators are mechanistically linked to MASH via insulin resistance, obesity, fat toxicity, and metabolic syndrome, diabetes, hypertension, and dyslipidemia, making them suitable stand-ins for modeling the disease's severity. A proxy-based model offers multiple advantages. It enables continuous, non-invasive monitoring, utilizes pre-existing longitudinal datasets, supports individualized trend tracking, and avoids the cost, time, and risks of clinical testing. However, limitations include reduced diagnostic precision compared to Goldstandard medical tests and the need for strong, scientific validation of each proxy's relevance to the target disease. Despite these constraints, the proxy model aligns well with the author's systems medicine approach, GH method, a math physical medicine tool, and large-scale, self-tracking dataset via his developed medical AI system, Chronic, on his iPhone, offering a scientifically grounded and operational framework for MASH assessment. It should be noted that proxy models are inherently less precise than Goldstandard methods, e.g., liver biopsy, FibroScan, and clinical validation remains necessary. Nevertheless, this modeling approach is both resourceful and grounded in solid pathophysiological reasoning. This study of MASH. This paper presents a proxy-based method to assess MASH risk by analyzing 5 key metabolic indicators. The author constructs a dimensionless MASH proxy index, MPI, that reflects the overall severity of metabolic dysfunction. The 5 components are: VF% as an indicator of central obesity, belly fat, in layman's terms, reflecting fat toxicity and a primary driver of hepatic steatosis; FPG, early morning, to reflect insulin resistance; EAG for chronic glucose exposure, associated with type 2 diabetes, and liver disease risk; SBP, systolic blood pressure, as an indicator of hypertension, a common comorbidity and contributor to systemic and hepatic inflammation; triglycerides, TG, for dyslipidemia, a hallmark of metabolic syndrome, that influences hepatic fat accumulation. All 5 variables are normalized using the following reference values: VF% divided by 13%, FPG divided by 90 mg per deciliter, EAG divided by 100 mg per deciliter, SBP divided by 120 mm mercury mHg, TG 150 mg per deciliter. Here, the division converts each metric into a unitless or dimensionless form, enabling consistent integration within the VMT energy model. These normalized values serve as both individual stressors and core components of the MPI. The study then applies the viscoplastic energy, VMT, model, using the MPI as the output strain and the 5 normalized variables as 5 input stressors, to quantify the liver-related physiological stress annually from 2010 to 2025. VMT methodology. MASH proxy index MPI equals the sum of VF norm, FPG norm, EAG norm, BP norm, and lipids norm, divided by 5. This MPI, a dimensionless composite score, represents the arithmetic mean of 5 normalized biomarkers and serves as a simplified but practical indicator of MASH risk. In the VMT analysis, the MPI is plotted on the x-axis as the output strain, while the 5 input stressors form the y-axis. The calculated VMT energy scores, area sizes of the enclosed 5 strain stress curves, represent the liver's annual metabolic burden over time. It should also be noted that this version of the MPI model assumes equal weighting of all 5 biomarkers. While practical, this may oversimplify the true physiological influence of each factor on MASH. Future iterations could explore assigning weights based on empirical correlation. Strength or mechanistic importance. To achieve a more accurate and nuanced evaluation, correlation results between inputs and MPI. VF% is 71%, FPG is 90%, E at G is 93%, SBP is -53%, TG is 43%. Observations: E at G, 93%, and FPG, 90%, show the strongest positive correlations with MPI, confirming that glucose control is the primary driver of MASH risk. VF%, 71%, also shows strong correlation, underscoring the impact of visceral fat on liver stress. TG, 43%, presents a moderate to low correlation, suggesting a lesser but still meaningful role, possibly limited by the lower frequency of his lipid testing. SBP, -53%, shows a negative correlation, potentially indicating a compensatory physiological pattern, where improvements in glucose and fat metrics, lower MPI, corresponded with temporary elevations in blood pressure due to unrelated lifestyle or stress factors. This inverse relationship likely reflects correlation rather than causation, and warrants further study. Aside from these findings, the statistical analysis yields limited additional insight. As always, it is important to caution that correlation does not imply causation, particularly in single-subject studies. MPI interpretations. MPI less than 1.0 indicates low MASH risk, observed from Y21 to Y25. MPI between 1.0 and 1.3 represents moderate MASH risk. MPI between 1.0 and 1.3 represents moderate MASH risk, observed from Y15 to Y20. MPI greater than 1.3 suggests high MASH risk with potential hepatic inflammation or fibrosis. Not observed in this case. The author's 11-year average MPI is 1.01, supporting a stable, low-risk MASH profile in recent years, largely attributed to disciplined lifestyle modifications. VMT energy contribution ratios. VF is 26%, FPG is 24%, E at G is 19%, SBP is 18%, TG is 14%. Interpretation. Visceral fat and FPG together account for 50% of the total modeled liver stress, underscoring the dominant roles of central obesity and insulin resistance in MASH pathogenesis. E at G, 19%, reflects the long-term impact of elevated glucose levels, reinforcing the importance of sustained glycemic control. SBP, 18%, indicates a moderate contribution to hepatic stress, likely mediated through vascular dysfunction and inflammation. TG, 14%, contributes the least, likely due to its lower sampling frequency relative to other variables. Conclusion: this study demonstrates the successful use of a proxy-based model to assess MASH severity through a systems-oriented, non-invasive approach. By integrating 5 widely available metabolic indicators into the MASH Proxy Index, MPI, the author presents a scalable and practical tool for liver health monitoring without requiring clinical procedures. The VMT energy model further enhances the framework by transforming static proxy data into a dynamic, stress-based system. It highlights the varying contributions of metabolic dysfunctions over time, with visceral fat and insulin resistance emerging as the most significant stressors. Combined MPI trends and VMT energy curves provide a comprehensive view of the author's liver-related metabolic improvement over the past decade. This methodology is particularly valuable for individuals with limited access to liver-specific diagnostics, or those managing chronic conditions independently. It promotes personalized, data-driven monitoring, supports preventive strategies, and encourages behavioral change grounded in quantifiable feedback. Looking ahead, this MPI proxy VMT energy framework could be adapted to other organ systems and metabolic conditions, advancing chronic disease management through an integration of data science, physics-based modeling, and systems medicine. It also lays the groundwork for developing intelligent self-monitoring tools, such as mobile apps, wearable devices and AI-driven platforms, that enable proactive health interventions. This article illustrates how chronic disease modeling can evolve beyond traditional clinical settings, by leveraging self-tracked data, mathematical models, and systems-level thinking. The author hopes this work provides a clear and consistent methodological example, and serves as a compelling case for the utility of proxy modeling in chronic diseases. Not limited to liver only, it aims to demonstrate how personalized, data-driven medicine can help bridge gaps in standard care, and empower patients in their long-term health journeys.